Determining the transformation matrix A from the coordinate equations. In our last lecture, we have seen that the elements of the transformation matrix Aij can be found by taking the dot product EI prime hat dot product with EG hat, where these EG hat are the basis vectors in the Cartesian coordinate system, and EI prime hat are the ones in the curvilinear coordinate system we want to move to. Now, if I write the displacement vector written in primed and unprimed coordinate systems, let's say in primed and unprimed, but this can be a transformation between two Cartesian coordinate systems as well. We're going to have the displacement vector, differential displacement vector, dr, written as dxi ei hat in the original Cartesian coordinate system, unprimed system. And now we're moving to another Cartesian coordinate system, dxi prime ei prime hat. And as with any vector that transforms between these two coordinate systems, I can write the primed coordinate system components, dxi prime, by multiplying dxj with the transformation matrix elements aij and adding over j. All right. So we also have the relationship between the prime system and unprimed system. x1 prime is equal to x1 prime, x1, which is a function of x1, x2, and x3. x2 prime is a function of the original unprimed coordinates x1, x2, and x3, and x3 prime is also equal to x3 prime, x1, x2, and x3. Or we can write xi prime, the primed coordinates, are functions of unprimed coordinates x1, x2, and x3. And in three-dimensional coordinate system, I would be 1, 2, or 3. For example, if I were doing a transformation between spherical coordinates and Cartesian coordinates, another orthonormal curvilinear coordinate system, R is related to x, y, and z as square root of x squared plus y squared plus z squared. Theta, the polar angle, is cosine inverse of z divided by square root of x squared plus y squared plus z squared, which is r. And phi, the azimuthal angle, phi, is tangent inverse y over x. So I have these coordinate transformation equations, for example, between Cartesian coordinates and spherical coordinates, which is another orthonormal system. Now, if I write dx1 prime, since x1 prime is a function of three variables, x1, x2, and x3, I know that this has to be written as partial derivative of x1 prime, which is a function of x1 and x2 and x3, with respect to x1, dx1 plus partial derivative of x1 prime, which is a function of x1, x2, and x3, with respect to x2 dx2 and partial derivative of x1 prime, a function of x1, x2, and x3 with respect to x3 multiplied by dx3. And this can be done also for the dx2 prime. So it's the same thing here, except that I'm going to get partial derivatives of x2 prime. So this would be x2 prime with respect to x1, x2 prime with respect to x2, x2 prime with respect to x3. All right. And also the same thing will happen for the x3 prime. So let me take this here. And now I'm taking partial derivatives of x3 prime. Del x3 prime del x1, del x3 prime del x2, and del x3 prime del x3. So that is to say, I'm taking dxi prime, where I can be 1, 2, or 3. I'm taking the partial derivative of xi prime, which is a function of x1, x2, x3, original Cartesian coordinates, with respect to xj, dxj, the repeated index is j, so that's a summation. And j can take values 1, 2, 3, using the Einstein summation notation. Now, the components in the prime system are related to the components in the unprime system, aij, dxj. So we already know this. Therefore, we're going to obtain these matrix elements aij to be you can see here, if dxi prime is aij dxj and it's also equal to del xi prime del xj dxj, this is recognized as the matrix element aij. So what I need to do is to write the coordinate transformation equation between the unprimed and primed systems and take partial derivative with respect to xj to find aij, the transformation matrix element. For example, if I look at my coordinate transformation between spherical and Cartesian and spherical coordinates, I would write del r del x. What is del r del x? It would be, now the derivative of square root would give me 1/2 to the power minus 1/2, and I would get 2x. So 2x and 1/2 will cancel, and I will be left with an x divided by r, and we know that x is equal to r sine theta cosine phi, so this would give me sine theta cosine phi, for example. So this would be the first transformation matrix element. If I look at del r del y, now it's all symmetric from this point on, it would be also equal to y over r, and this would give me this time sine theta sine phi, because y is equal to r sine theta sine phi. And if I look at del r del z, which is also z over r, and z is equal to r cosine theta, so this would give me cosine theta. So the first three matrix elements here would be sine theta cosine phi, sine theta sine phi, and cosine theta. So if I start writing my transformation matrix between the Cartesian coordinates x, y, z, and the prime coordinate system would be r theta phi, then I would have x is equal to, so I would have sine theta cosine phi, sine theta sine phi, and cosine theta is the first three matrix element. That would give me the transformation between x and r, y and r, and z and r. So here we have gone through the exercise of determining the transformation matrix elements, which we realized could be obtained by taking the dot product or inner product between ei prime hat and ej hat. When I go between two Cartesian coordinate systems, unprimed and prime coordinate systems, I could also determine the transformation matrix elements from coordinate equations, which I realized when I wrote the displacement vector dxi ei hat and dxi prime ei prime hat. And here you can see that dxi, if I, for example, take the dot product with ej prime hat here, you would get the transformation matrix element. For example, for this one, you would give dxi prime. So if this is dxj prime, ej prime hat, ej prime hat, ej prime hat, dot product would give you 1, and this would give you the transformation matrix element. So dxi prime is aij dxj. So I can always write it this way. But instead of doing that, if I write the coordinate transformation equations, and when I write dx1 prime or dx2 prime or dx3 prime, or in other words dxi prime, it's del xi prime del xj dxj. And because of that, and since these two equations are the same, I recognize the transformation matrix element aij as del xi prime del xj.